say that that C in that reaction is a 2, then we would square that concentration in molarity. The concentrations at equilibrium. So let's plug those in. The smaller the number, if we had a tiny, tiny number, the reaction would barely proceed at all. This video is about equilibrium constants. So first of all, the symbol for equilibrium constant is Kc. Anytime you see a K, that represents a constant. And then that little subscript C represents concentrations. So we're going to use this as an expression of the concentrations of all the participants in the reaction at equilibrium. So let me show you how to write that expression. This looks a little complicated, but it's not. So let's say we have this reaction here, A and B going to C and D. And that is reversible, right? We've got arrow this way, arrow that way. So it's a reversible reaction. And let's assume that these are all either gases or aqueous, okay? Gases or aqueous. And so if a substance is a gas or aqueous, we're going to include it in the expression. So on the numerator, on the top, we're going to put the products. And the way we'll write that is we have the concentration of C, whatever substance C is. The brackets mean molarity. Okay, brackets mean molarity. It has to be brackets, not parentheses. And then we're going to raise that to the exponent that is the coefficient. So let's say that that C in that reaction is a 2, then we would square that concentration in molarity. And so on. So we're going to multiply the products. It doesn't matter if there's 1 or 2 or 7, right? The products on the top, the reactants are on the bottom. Now, very important, only include substances that are gas or aqueous. If it's a solid or a liquid, leave it out of the expression. So that's how you write it. Here's an example. Here's a reaction at equilibrium. And so let's write the Kc expression. Well, the product here, both gases, right? Gas, gas. So everybody is included. On the top, we have NO2 brackets, and then we're going to raise that to the second power because of that coefficient. And then on the bottom, we have N2O4. Now, in this problem, we're actually given the concentrations at equilibrium. So let's plug those in. So at equilibrium, our NO2 is 0.050 molar, and I'll square that, and then the N2O4 is 0.54 molar. Okay, and so you just crunch the numbers, do the math. 4.6 10 to the minus third. So that is the value for the equilibrium constant at some temperature, at that temperature. All right, let's continue. Kc, the magnitude of it will tell you something about the equilibrium. So if it's really small, that says the reactants are favored, right? Because a small number, the denominator would be larger, greater concentration. And then if Kc were larger than 1, the product would be favored. Now, here is another expression. This, you might have figured this out. A Kp is where we're using partial pressures. Okay, so partial pressures of substances. So here we've got gases, right? All gases in this reaction. And you write the expression exactly the same. And that would be a Kp. Now, let's talk about, again, the magnitude. So if you have a large number, like 10 to the 4th, that means that the forward reaction is favored. So a big one means the forward is favored. Okay, that makes there's more product than reactant. And then if you have a small number or a really small number, then and that makes sense. So the smaller the number, if we had a tiny, tiny number, the reaction would barely proceed at all, right? So it would be very heavy to the reactant side. All right, one more thing that we need to do is, how do you find a K for a reaction that maybe you can't find in a table? So let's say we have this hypothetical reaction of A and B, and I have a very simple Kc expression of 4 for this reaction at a temperature. Well, if you reverse a reaction, here's our procedure here, we're going to take the inverse of K. So if we reverse this reaction, the K for this expression would be 1/4 or 0.25. Okay? Now, what if we had a reaction that looked just like it, but it was doubled? Everything was doubled. we would square that. And so K would be 4 squared, or 16. All right, and then last of all, if we halved a reaction, what do you think? Well, we would take the square root of that K, and that would be 2. So that's just a very simple way to manipulate and get the K for a desired reaction from something that you already had. Okay. Now, one other thing that we can do is if we add two reactions, let's say we had two reactions and we add them and we get something like this. If I add these two reactions, I get A plus B is in equilibrium with C. And I needed to know the K for this reaction. Well, if you add two reactions, you multiply their equilibrium constants. So this value would be the product of those two. So these are a couple ways just to understand equilibrium constants. They are found in tables. You can look these things up. A lot of times they're given in the problems, and you may need to use them to solve for concentrations, which we'll get into in the next video.